This is John Black, Super Chemist. This is from a playlist called New and Updated Frame of Reference. Part 1 in this individual video is about what is a frame of reference. A frame of reference is just a place where you get your point of view from. A place where you perceive the world. Best way to learn about frame of references is to give you examples. So here's your first example. You got this house here. You can see the door right there. You have 3 frames of reference. What's a frame of reference? It's a place. Here's a purple reference, red reference, blue reference. The reference frame is this box, these boxes that they are in. And what do they see this door when they look at it? This, from the frame of reference of the purple man, there is no door. You can see the line, because everything, you can see this brown dotted line. Anything on this side of that line, you can't see here. They can't see around. He cannot see any doors. According to his frame of reference, there is no door. According to the red frame of reference, he gets a direct line at that door. He can see it's 3 feet wide. This blue man is barely past this line right here, so he has a different angle. His angle, he can only see that the door is 2 feet wide. So from the blue frame of reference, the door is 2 feet wide. From the red frame of reference, it's 3 feet wide, and the purple frame of reference, there is 0 door. There is no door. Are any of these people lying? No, they're not lying, because this guy right here, the purple guy, he's not saying there isn't a door. What he's saying is, from the place where he gets his point of view, there is no door. He doesn't see it. The red man doesn't say that the door is 3 feet. He says from his place, from his point of view, the door is 3 feet. And the blue man says from his place, from his point of view, the door is 2 feet. They're all telling the truth. The thing about frames of reference, though, is one about when you're moving. Like this man right here, he's moving in a train. He's going left to right. You can see the velocity arrow. He's got a ball. What if he throws that ball up in the air? Well, the train is moving. What will he see? He will see this. It'll be right in front of him, though. It'll go up and down. Just like you would be standing, like this guy is standing on the earth. Just like when he throws a ball up, what happens? It goes straight up, comes straight back down. Why does that happen anyway? It's because if they all, let's say they're all going 500 miles an hour. Well, if you throw the ball up in the air, it's still going 500 miles an hour. Just because you threw it up in the air, it doesn't automatically just stop and go 0 miles an hour. No, it keeps going 500 miles an hour, because why wouldn't it? That's only logical. So if the ball and the train are moving at 500 miles an hour, and he throws it up in the air, and the ball keeps moving 500 miles an hour, the ball is just going to stay in front of him, just going up and down as he throws it up and down. But I want you to think about it. The frame of the reference of the man standing on earth, it's not moving in the train. What will he see? Because the ball will be here. He throws it up, but the thing is moving. The train is moving, see? And then the guy will be over here and catch the ball. That makes a palabra. Okay, so you might say, well, that's the frame of reference that's correct. That's what reality is. Let's say that this train is going perpendicular to the way the Earth is spinning, and some guy is out in space looking down on you. Now, as you throw the ball up, you're moving, you're spinning, so it elongates the palabra and kind of makes it, and you're moving into the palabra as the Earth spins, so it stops here instead of it being equal, on the same horizontal plane. Look at this, it's way up here. Doesn't look the same. They're all right because they're not saying what's happening. They're saying what their physics or their eyes or their perception, what they perceive, their point of view. They're just telling you what their point of view is. And their point of view is right. This guy perceives the ball to go up and down. This guy perceives the ball to do palabra. This guy perceives it to do this. Because they're not saying this is reality. This guy isn't saying this is reality. This isn't saying this is reality. What they're saying is, in their own frame of reference, this is reality. It's what they perceive in their frame of reference. Now, what if the man was on the train and he dropped a ball? To prove my point, we're going to watch a video. First, we're going to watch what does the man standing still on Earth see as this train goes by and the ball drops.
I'll show you this again. This time there'll be a line on the film so that you can see the path. think that you can see that the path of the ball is a parabola.
Notice how he saw a parabola. Now let's see what the man, let's say if you were on the train with this guy dropping the ball, what would he see?
Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point.
Notice in the frame of the train, the ball just goes straight down. It doesn't, you can't see the parabola.
In the moving frame of reference, I think you could see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity. I'm going to do the experiment once more, and this time I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference frame. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, then I think perhaps it was harder for you to realize that you were in a moving frame of reference. The important thing to realize here is that all frames of reference moving at constant velocity with respect to one another are equivalent.
See, look at this guy. You got a purple guy and a green guy. They're both, you can see, 2 lines. This one's 2 lines long, green, 2 lines long to purple. But when the purple looks at the green guy only looks like he's 1 line tall. And the green guy looks at the purple guy, and it looks like he's 1 line tall. Who's right? We know they're 2 feet tall. We can see this one's 2 feet, and this one is 2 feet. They're both right, because neither one is saying that the other man is the other man is 1 feet or 1 line tall. They're saying that from their frame, they perceive the other person to be 1 foot tall. They're not saying that they are 1 foot tall. They're saying from their frame, they perceive the other one as being 1 line tall. What about on the Earth? Let's say you're standing on Earth. We know the Earth is orbiting around the Sun. All of our physics proves that we are orbiting around the Sun. But if you use common sense, the Sun, let's say the galaxy is moving. Okay, we don't know which direction exactly, but let's just say arbitrarily it's moving in the y direction. So the Sun would be going up, and the planet Earth would also be going up. But the planet Earth would also be orbiting at the same time. And you can see, what does that do? That creates a corkscrew. So technically, we are not orbiting the Sun. We are corkscrewing the Sun. Are we lying? No, we're not lying. Because when we say that we orbit the Sun, we're not saying that that's reality. We're saying from our frame of reference, there's no physics that can prove otherwise. You would have to leave the plane of the galaxy pretty much so that you can look over and see that the galaxy is moving and the Earth is moving with it, plus the Earth is orbiting. Just like this purple guy up here. He can't know because he says there's no door. Yeah, because his whole universe, his whole frame is this box. This guy in the Earth, his whole frame is the Earth. Just like this guy, he can't know that it's actually going in a parabola because he'd have to leave the train and leave his frame of reference. What about these 2 spaceships? They're going at constant velocity. One's going this way, this one's going that way. They're both looking out their window. You can't see this guy because he's on the other side looking at him. They're looking at each other. How do they know if they're going constant velocity, they're both floating in outer space? The whole universe is gone. Anytime you do an experiment, a thought experiment like this, remember, the entire universe is gone. It's just these 2 ships. So they have no trees or whatever on Earth or any planets or anything outside to give them a cue on what's going on. If they did, like if this was a car and this was a person on Earth and the car was moving this way, yeah, if you can look out your windows, obviously you can see who's moving and who isn't. So that's idiotic. But if you are in outer space and both people in both ships are floating, they're constant velocity, inertial. So the thing about this is when you are inertial like this, like we said, if everyone is moving at the same, if it's 500 miles an hour, if they're all moving 500 miles an hour this way, you can't tell the difference between just standing still and moving at constant velocity, because everything will just follow you. How could you tell? You can't tell. You can never figure it out. So this guy right here, if he thinks he's standing still, he's going to look at this and he's just going to see this spaceship going by while he stands there. And this guy right here, he's going to think he's standing still, or he could think it if he didn't know he was. If he just was blacked out and he woke up and he didn't know who he was and he amnesia and he's floating, he could be like, "Oh, I don't know if I'm constant velocity or I'm standing still." But he's going to look at this spaceship, and all he's going to do is see a spaceship flying by while he's just floating there, not moving, not having any forces acting on him, so he knows that he's not accelerating. But that's what it's all about, is these couple things I just said, because if you can't tell the difference between standing still and constant velocity, then that's going to come into a lot of problems. So what if we have these different frames of reference? Why do we care? It's because of measuring stuff. We like to measure stuff, okay? And if we measure stuff from one frame compared to another frame, we might get no door, we might get 3 feet, and we might get 2 feet, depending on our frame of reference. So we need to have extra math to tell us what reality is. Like the reality is the door is 3 feet wide. That's reality. So we have to take into account that he is at an angle and do some more math here so we can figure out what the real door length is. So look over here. We got a man standing here at 0 mile an hour. We got a 50-mile car going to the right, and we got a spaceship, no rockets on, so these are all constant velocity, moving at 500 miles an hour this way to the left. This is what the man perceives from his frame of reference. Standing here, he sees the car going 50 miles an hour to the right, and a spaceship 500 miles to the left, 100 miles per hour to the left. That's his frame of reference. That's true. Keep in mind, this is a BS thingy here. You should be having 3 spaceships in outer space, and you can't see any. The universe is gone. Okay, so keep that in mind. You can't just say, "Oh, he just look out the car and see what's going on," because these are supposed to be really 3 spaceships that are in outer space with no universe to get any cues from. So the car thinks he's standing still because he's going at constant velocity, and then he looks at the spaceship. The spaceship is going this way 500 miles an hour, but he is going the opposite direction, 50 miles an hour. So he sees this guy going at 550 miles an hour to the left. He sees the man going at 50 miles an hour this way. Well, what about the spaceship? From the spaceship, he thinks he's going 0 miles an hour. You got to imagine that these are all spaceships, and they all got knocked out, and they all have amnesia, and they wake up, they don't know where they're at and what's going on. So he thinks that he's going 0 miles an hour. He looks at the car, and it looks like he's going 550 miles this way. 50, you add these up. Then he sees this guy. He says, "Oh, he's moving 500 miles an hour that way." Which frame of reference is correct? All of them are correct because they're not saying what reality is. They're just saying what they perceive from the place where they get their point of view. This is why relativity comes into play.
Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving.
The reason you know is because the man in the background is just standing there. You can tell he's not moving. He's not walking.
The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume.
This represents a frame of reference, just 3 rods stuck together so that each is at right angles to the other 2.